In this lecture, I will discuss the concepts of kinetic energy and work, and also the work done by several specific forces, and then I will do several examples to illustrate the concepts. First, let's define energy. Energy is required for any sort of motion. Energy is a scalar quantity assigned to an object or a system of objects. Energy can be changed from one form to another, but energy cannot be created out of nothing or destroyed completely. Examples of conversion of energy from one form to another would be electrical energy being converted into thermal energy by cooking appliances, or electric energy being converted into mechanical energy of motion, heat energy being converted into mechanical energy of motion, and so on and so forth. Energy is also conserved in a closed system, which means that the total amount of energy of all types is always the same. What is a closed system? A closed system would be a collection of bodies that are isolated from their surroundings and do not interact with them. Those bodies can only interact between themselves or with each other. And so in this sense, no energy can come into the system from outside, and no energy can leave the system. And then the total energy of the system will always be conserved. In this chapter, we are going to discuss one type of energy, and that is the kinetic energy. And we are also going to discuss one method of transferring energy, and that is doing work. Let's define kinetic energy. Kinetic energy is the energy of motion. It is associated with objects that have certain mass and also velocity. The faster an object moves, the greater its kinetic energy. Kinetic energy is zero for a stationary object, since the velocity is zero. For an object with velocity v, well below the speed of light, the kinetic energy is defined as the product of the mass, the velocity to the second power, divided by 2. The label for kinetic energy is capital K. The unit of kinetic energy is a joule, where 1 joule is equal to 1 kilogram times 1 meter squared divided by 1 second squared. From those units here, you can see that when you're calculating the kinetic energy of an object, the mass of this object must always be converted into kilograms, and the velocity of the object must always be converted into meters per second. If you forget to do the conversions, then the value that you will get for the kinetic energy will be off, and it will not be in joules. For a moving object, when the velocity changes, that will result in a change of the kinetic energy of the object. The kinetic energy changes by transferring energy into the object or to the object or from the object, and this transfer is happening by applying force, and this force does work. The work W is energy transferred to or from an object by means of a force acting on the object. Energy transferred to the object is positive work, and energy transferred from the object is negative work. So, to do work on an object, energy must be transferred. For example, throwing a baseball does work, because energy is transferred to the baseball when it's being thrown. But pushing on an immovable wall does not do work, because no energy is being transferred since the wall doesn't move. Here is a visual drawing of the concept of force applied to an object, which result in the change of kinetic energy. My object is a bead that is confined to move along a straight horizontal wire. The object, the bead, moves under the action of this force F, which is directed at an angle phi with respect to the wire. So, under the action of this force, this bead will be moving along the wire with some initial velocity v0. And so I can assign kinetic energy initial to this bead, calculated as the product of the mass of the bead, the initial velocity to the second power divided by 2. Under the action of this force F, the bead is going to displace a certain distance d, and because the bead is under the action of this force, the velocity at the end of the displacement will be different, and so therefore the kinetic energy at the end of the displacement will also be different. Let's call this kinetic energy Kf. Now, kinetic energy final is equal to the product of the mass of the bead, the velocity v squared divided by 2. So, under the action of this force F, the kinetic energy of this bead changed from that initial value to that final value. Now let's find an expression that gives us the relationship between the change in kinetic energy and the work done by that applied force F. To find the relationship, let's use Newton's second law, which states that force is equal to mass times acceleration, and since the motion of the bead is along the x direction only, one-dimensional motion, Newton's second law for the bead will read that the x component of the force is equal to the mass of the bead times the acceleration of the bead in x direction. Another relationship that I can use to find the relationship between the change in kinetic energy and the applied force is this kinematic equation, which relates the final velocity, initial velocity, acceleration, and displacement. So from Newton's second law, I can express the acceleration in terms of the applied force and the mass of the bead, and then substitute for the acceleration here and solve for the product of force, time, and distance. So after substitution, the equation looks like so, and then moving some of the terms around so that I have the product of force and displacement left on the right-hand side and everything else on the left-hand side, I get 1/2 mv squared minus 1/2 mv0 squared is equal to fx times d. The first term on the left side is the final kinetic energy of the bead. The second term on the left-hand side is the initial kinetic energy of the bead. And so we know that when the kinetic energy changes for an object, work must have been done by some force. So that means that the right-hand side here must be the work done by that force Fx. So the work done W is equal to the product of the force Fx times the displacement d. Just to remind you, when I say the force Fx, I mean the x component of the force F that was applied on the bead. Now we're ready to state the definition of work in terms of force and displacement. To calculate the work of a force that a force does on an object as the object moves through some displacement, we use only the force component along the object's displacement. The force component perpendicular to the displacement does zero work. So for an angle phi between the force and the displacement, the work done, W, is equal to the force times displacement times the cosine of the angle between the two. Remember from chapter 3, vectors, that we discussed the meaning of this type of relationship. Going back to my example with the bead on the wire, the force applied to the bead is force F, like so. The x component of the force lies along the wire, and it is given by Fx equal to F cosine of phi. So if I multiply that component by the displacement d, I'm going to get the expression for the work, like so. Now, let's remember also that this type of relationship was the definition of a dot product. Just to refresh your memory, the dot product between two vectors A and B, with an angle phi between the two, is defined as the magnitude of A times the magnitude of B times the cosine of the angle between the two. So therefore, the work done by the force is simply equal to the dot product between the force and the displacement. A few important notes about the concept of work. First of all, the force that is acting on the object is constant. The object is particle-like, or in other words, rigid. And finally, work can be positive or negative or even zero. Let's look into the signs of work depending on the orientation of the applied force and the direction of the displacement of the object. In the first example here, I have my bead moving to the right under the action of this force F. The force makes an angle phi with the displacement. So by definition, the work done by this force is the dot product between the force and the displacement, which is calculated as F cosine of the angle phi times d. When the angle phi is less than 90 degrees, then the cosine of that angle will be a positive number, which then gives us a positive value for the work done by the force. In the second example, the applied force is perpendicular to the displacement. So from the definition of work, which is the force times the displacement in a dot product, we get F cosine of phi times d. When phi is equal to 90 degrees, the cosine will be equal to 0. Therefore, the work done is 0. So for a force that is perpendicular to the displacement of a moving object, the work done by that force is 0. A prime example of that result is the centripetal force that acts on an object that is moving along a circular trajectory. The centripetal force always points towards the center of that circular trajectory, and it is perpendicular to the infinitesimal displacement of the object at any moment as it's going around this circle. So that means that the centripetal force does no work on an object that is undergoing uniform circular motion. In the third example here, the force F is at an angle phi, like so, with respect to the displacement. So again, the work done by this force is F cosine of phi times d. But now notice that the angle between the force and the displacement is larger than 90 degrees. That means that the cosine of that angle will be less than 0, a negative number, which then gives us the work to be a negative number. Let's summarize those three examples in the following statement. A force does positive work when it has a vector component in the same direction as the displacement. And it does negative work when it has a vector component in the opposite direction. It does zero work when it has no such vector component. For two or more forces, the net work is the sum of the work done by all the individual forces. And there are two methods to calculate the net work. We can find all the works done by individual forces and then sum them. Or we can take the vector sum of all forces and find the net force acting on the object and then calculate the net work only one time. The units for work are joules, and that makes sense because the work done by a force is equal to the change in kinetic energy of the object. And since the kinetic energy is measured in joules, that then means that work also will be measured in joules. The relationship between the work done by a force and the change in kinetic energy is given by the work-kinetic energy theorem. The work-kinetic energy theorem states that the change in kinetic energy delta K which is equal to the final kinetic energy of an object minus the initial kinetic energy of the object, is equal to the work done by the net force. So change in kinetic energy is equal to net work done. I can also rearrange the terms in this statement here to find an expression for the final kinetic energy. The final kinetic energy is equal to the initial kinetic energy plus the net work done. Depending on the sign of the work done, positive, negative, or zero, we can then deduct, based on that, whether the final kinetic energy will be more, equal, or less to the initial kinetic energy. When the work done is a positive number, this sum will be larger than the initial kinetic energy, so the final kinetic energy will be bigger than the initial kinetic energy. This is the case when force is applied, or at least a component of the applied force is in the direction of the displacement of the object. When the work done here is zero, which is the case of a force applied perpendicular to the displacement of the object, the final and initial kinetic energies are equal. And finally, when the work done is a negative number, which is the case when the applied force has a component opposite to the displacement of the object, then the final kinetic energy will be less than the initial kinetic energy. Let's summarize that statement with the following examples. When the work is positive, that means that the applied force has a component that is in the same direction as the displacement. And so in this case, the kinetic energy final will be larger than the kinetic energy initial. In the case when the work done is zero, which is the applied force is perpendicular to the displacement of the object, the two kinetic energies, final and initial, are equal. And finally, when the work is negative, which means that the applied force has a component that is in opposite direction to the displacement of the object, and the final kinetic energy is smaller than the initial kinetic energy. Let's now discuss the work done by some other forces. First, let's talk about the work done by the gravitational force. Consider an object with mass m that is tossed up in the air, and it's under the action of only the gravitational force. So the displacement of this object is vertically up, but the gravitational force is directed vertically down towards the center of the Earth. The work done by the gravitational force in that particular case will be simply the gravitational force times the cosine of the angle between the displacement and the gravitational force times the displacement itself. Well, the angle between the displacement and the gravitational force here is 180 degrees. So therefore, the work done by the gravitational force when the object is traveling up in the air is negative. The second possibility is for the object to be free falling towards the Earth. In this case, the displacement is vertically down and the gravitational force is also vertically down. So then the work done by the gravitational force will be the gravitational force times the cosine of the angle between the displacement and the gravitational force, which is 0 degrees, times the displacement. This results in a positive work done by the gravitational force. The work done by the gravitational force is simply the mass of the object times gravitational acceleration times the displacement times the cosine of the angle between the gravitational force and the displacement. So, for an object that is rising, the work done by the gravitational force will be equal to mgd, cosine of 180 degrees. This example here, which is equal to mgd times minus 1, or that is negative mgd. So, negative work done by the gravitational force, as I discussed in the previous slide. For a falling object, the work done by the gravitational force is equal to mgd times cosine of 0 degrees. This example here. Cosine of 0 is equal to plus 1, so the work done by the gravitational force is a positive number, mgd. Now let's consider that the object is not only under the action of the gravitational force, but also under the action of an external applied force, F. First, let's have the object displacing vertically up. The applied force is also directed vertically up, and of course, the gravitational force is directed down. So, in this case, the applied force F is going to do positive work because it is directed in the same direction as the displacement, and as we already know, the gravitational force in this case does negative work. The second possibility is for the object to be falling down, and as the object is falling down, an external force F acts on the object vertically up. The gravitational force obviously is acting straight down, and the displacement of the object is also vertically down. In this case, the applied force F does negative work because the angle between that force and the displacement is 180 degrees. And the gravitational force does positive work because the angle between the gravitational force and the displacement is 0 degrees. So then I can try and find the relationship between the change in kinetic energy of this moving object and the work done by the applied force and the work done by the gravitational force. And so, the change in kinetic energy, which is final kinetic energy minus initial kinetic energy, will be equal to the work done by the applied force plus the work done by the gravitational force. And now, depending on how the object is moving, up or down, those two quantities will come in with positive or negative signs accordingly. For an object that starts at rest and ends at rest, the kinetic energy is final and the initial will be equal to 0, which means that the sum of the two works, the work done by the applied force and the work done by the gravitational force, will be equal to 0. Or in other words, the work done by the applied force will be equal to minus the work done by the gravitational force. Similar result is achieved when the initial and final kinetic energies are equal, but the object is not necessarily stationary. So the object is moving vertically, and the initial kinetic energy at some point is equal to the final kinetic energy at another point, in which case the work done by the applied force is again going to be equal to minus the work done by the gravitational force. Or in other words, the work done by the applied force is equal to minus mgd cosine of phi, and this relationship applies for any path. What does that mean? So consider this object with mass m at this initial position. This object gets to this final position, and that can happen along two different paths. Path number 1 and path number 2. When the object gets from the initial position to the final position along path number 1, the object initially moves horizontally that much distance. During that portion of the motion, the applied force and the gravitational force do no work on the object because they're perpendicular to the displacement. And then during that portion of the path, the gravitational force and the applied force will do work on this object. Now, the object is going to get from the initial position to the final position along path number 2. As the object goes along this vertical displacement, both the applied force and the gravitational force will do work. But then when the object displaces from here to the final position horizontally, the two forces will do no work on the object. So, the vertical displacements along paths 1 and 2 are equal in magnitude, and so since the applied force and the gravitational force remain constant, the work that is done as the object moves along path 1 from the initial to final position should be equal, or is equal, to the work done as the object moves along path 2 from the initial to the final positions. So this illustrates, in a very idealized situation, the meaning of the independence of path for the work done by the applied force. There is one more force to discuss in terms of the work done by that force, and that is the spring force. A spring force is a variable force from a spring. A spring force has a particular mathematical form, which we will see very shortly. And of course, many forces in nature have this form. And they're not necessarily spring force, but they have the same form. So the example here is a spring that is attached at one end, which is fixed, and at the free end we have attached a block. Initially, the spring is in its relaxed state, which means it is neither compressed nor stretched. And then an external force is applied on the block to pull the spring to the right to stretch it, or to push the spring to the left to compress it. The amount of stretch or compression is equal, and we call it x. And as the spring is being moved from its equilibrium position, the block itself will displace a distance d. So when the spring is stretched or compressed, a restoring force is generated by the spring. And this restoring force is the spring force. When the spring is stretched, the restoring force wants to return the spring back to its equilibrium state or relaxed state. When the spring is compressed, the restoring force arises such that it wants to stretch the spring until it gets to its equilibrium or relaxed state. This restoring force, or the spring force, is given by Hooke's law, which states that the spring force is proportional to the displacement as vectors, and the constant of proportionality is k. The minus sign here indicates the fact that the spring force is always directed opposite to the direction of displacement. So here the displacement is to the right, the spring force is directed to the left. Here the displacement is to the left, the spring force is directed to the right. So the negative sign represents the fact that the force always opposes the displacement. The spring constant K is a measure of the stiffness of the spring. The units for the spring constant are newtons per meter. And so from the units here, you can see that the displacement must always be measured in meters or converted in meters before you can calculate the spring constant for a particular spring. A spring with small spring constant will be more pliable, will be easier to stretch or compress. A spring with larger spring constant will be stiffer, meaning it's going to be harder to stretch or compress. The spring force is a variable force. It is a function of position, and it exhibits a linear relationship between the force and the displacement. So the spring force is a function of position. Typically, we discuss problems that are one-dimensional. So therefore, we are going to rewrite the expression for the spring force in component form for the x-axis, and that is that the x component of the spring force is equal to minus the spring constant times the amount by which the spring was stretched or compressed. Since the spring force is a variable force, in order to find the work done by the spring force, we must integrate. By definition, the work done by a variable force is equal to the integral of the force times the x, and this is for one-dimensional case. So how can we deal with the fact that the force is variable in the case of a spring? Well, we can split the displacement of, or the amount by which the spring is compressed or stretched, into very small length segments, over the length of which the force is essentially constant. And so then we can calculate the force for each segment, and that would be simply this force. Now, if we add all those forces for each of the segments together, that becomes a sum. And when we have a large number of terms in that sum, this sum simply becomes an integral. And so then that integral will look like so. So solving this integral gives us an expression for the work done by the spring force, which is given with this formula here. The work done by the spring force is equal to a term that depends on the spring constant and the initial position of the block to the second power minus a second term which also depends on the spring constant and the final position of the block to the second power. The work done by the spring force can be positive or negative, and then it also depends on the net energy transfer. The work Ws is positive if the block ends up closer to the relaxed position than it was initially, and it is negative if the block ends up further away from the relaxed position than it was initially, and it is equal to 0 if the block ends up at the same distance from the relaxed position, which means no displacement. I want to show you the derivation of the formula for the work done by the spring force. So the work done by the spring force is this integral right here, and the spring force is by definition given by Fx is equal to minus Kx. What I need to do is I need to substitute here with the magnitude of the spring force. So that means that I'm going to take the spring force with a positive sign here, and then the integral becomes minus an integral from the initial to final positions of Kx dx. What are the initial and final positions? Those are the limits of the integration. So let's say that the block was here at this initial position, it displaced a distance d to this final position, and then the minus here corresponds to the fact that the spring force is opposite to the direction of the displacement. And so, to do the integral, I used a rule for integration that is shown in Appendix E in the textbook. And that rule says that an integral of x to the power of m of dx is equal to x to the power of m plus 1 divided by n plus 1. So in my example, the power m is equal to 1. The power here is equal to 1. So when I do the integral with respect to x, I'm going to get x to the second power divided by 2. And so then this integral becomes minus kx squared divided by 2 with the limits of x initial to x final, or that is minus kx final squared divided by 2 minus kx initial squared divided by 2. Here, what I did is I replaced the variable with the two limits. The first term contains the upper limit, the second term contains the lower limit, and I subtracted the term with the lower limit from the term with the higher limit. And then accounting for this minus sign, I get the expression for the work done by the spring force. Now I can also set the initial position to be equal to 0, in which case the work done by the spring force is simply minus 1/2 kx squared. And then, just like in the discussion of the work done by gravitational force, if if another force is applied to the block attached to the spring, and the initial and final kinetic energies of the block are equal or 0, the work done by the applied force will be equal to minus the work done by the spring force. If a block that is attached to a spring is stationary before and after displacement, then the work done on it by an applied force displacing it is the negative of the work done on it by the spring force. Lastly, let's discuss one more quantity associated with the concept of work, and that quantity is power. Power is the time rate at which force does work. In a way, this is the efficiency with which work was done, because work can be done in any number or any amount of time, but once we have knowledge of how long it took for the work to be done, then we sort of know the efficiency with which that work was done, and that efficiency is the power. A force does work W in amount of time delta T. So if I take the ratio of the work done by the amount of time necessary to do that work, that defines the average power due to the force. The average power is, again, the work divided by the time it took to do that work. If I wanted to know how much power was developed at a certain moment of time, then I must calculate the instantaneous power. The instantaneous power is calculated as the limit when the time interval approaches 0 of the average power, or this is just the time derivative of the work done. So the instantaneous power is the time derivative of the work done. In the metric system, the units for power are watts, and 1 watt is equal to 1 joule per second. If I multiply the average power by the time interval that it took to develop that power, that gives me the work done, which in other words is also the energy change that happened due to that work done. And so the units for energy can be written as the units for power times the units for time, or in other words, watt hours, or the more common one, kilowatt hours. We can even go one step further from the expression for the instantaneous power, the time derivative of the work done. I can substitute for the work, I can substitute F cosine of phi times x, which then becomes F cosine of phi dx dt. This simply is the expression for the work done by a force, or rather the definition of a work done by a force, used to replace said work here. Okay, so then notice that I get a term that is the time derivative of the position, and if you remember from the previous chapters, that is defined as the velocity of the moving object. So the instantaneous power is simply equal to force times velocity times the cosine of the angle between the two vectors, or in other words, the instantaneous velocity can also be calculated as the dot product between the force and the velocity of the moving object. Let's do several examples using the concepts discussed in this chapter. The first example is work done by a constant force. Steve exerts a steady force of magnitude 210 newtons on a stalled car as he pushes it a distance of 18 meters. The car also has a flat tire, so to make the car track straight, Steve must push at an angle of 30 degrees to the direction of motion. How much work does Steve do? And the second part of the question is, Steve pushes a second stalled car with a steady force, F, given with this unit vector notation. The displacement of the car is S, given with this unit vector notation, how much work does Steve do in this case? So for the first part of the question, this is the sketch of the situation. This is the car. Steve applies a force of 210 newtons at 30 degrees to the horizontal, or the direction of motion of the car. The car displaces a distance s of 18 meters. And so the question is, what is the work done by Steve in this case? The work done is calculated as F times S times cosine of phi. So note that here, since I'm using an example from a different text, the displacement is labeled with S instead of D. So keep that in mind. And here I have all the necessary information to calculate the result. So this will be equal to 210 newtons times 18 meters times cosine of 30 degrees. That gives me 3.3 times 10 to the third power joules. Now let's look at the second part of the question, and that is, if Steve pushes with a force given in unit vector notation by this vector, and the displacement of the car in unit vector notation is given by this vector, how much work does Steve do? For this second part of the problem, I'm going to use the definition of work in terms of dot product between the applied force and the displacement. So work is equal to F dot S. And let's refresh the memory on the definition of a dot product. So for two vectors A and B in a dot product, the result is equal to the sum of products of the components of the two vectors. So A dot B is equal to AX times BX plus AY times BY plus AZ times BZ. So in our particular problem, the work done is equal to 160 newtons I minus 40 newtons J dot 14 meters I plus 11 meters J. From the above definition right here, we get that the work is equal to 160 newtons times 14 meters minus 40 newtons times 11 meters. And this is equal to 1.8 times 10 to the third power joules. So as you can see from this problem, when the information provided is for the force and for the displacement is in terms of magnitudes and the angle between the two vectors, then we use that definition of dot product for to calculate the work done. And when the force applied and the displacement are provided in unit vector notation, then we have to go with the dot product definition of work to calculate the result. Now let's do an example problem about work done by several forces. A farmer hitches her tractor to a sled loaded with firewood and pulls it a distance of 20 meters along level ground. The total weight of sled and load is 14,700 newtons. The tractor exerts a constant 5,000 newton force at an angle of 36.9 degrees above the horizontal. A 3,500 newton friction force opposes the sled's motion. Find the work done by each force acting on the sled and the total work done by all forces. Here is a drawing of the problem. So here's the tractor, here's the load, here's the sled, and this here is the free body diagram of all forces that act on the sled. So we have the applied force from the tractor, 5,000 newtons at 36.9 degrees. We have the weight of the load, which is 14,700 newtons. We have a normal force straight up, and then we have a friction force of 3,500 newtons opposing the motion of the sled. So we need to find the work done by each force acting on the sled and the total work done by all the forces. The total work done on the sled is the work done by the weight, the normal force, plus the work done by the normal force, plus the tension in the chain, plus the work done by the kinetic friction force. The work done by the weight and the normal force on the load is equal to 0 because those two forces, the weight and the normal force, are perpendicular to the displacement of the sled, which is horizontal like so. So those two are zeros. All we need to do is calculate the work done by those two forces, the force along the chain and the kinetic friction force. The work done by the force in the chain is equal to that force times the displacement times cosine of 36.9 degrees. Well, that is 5,000 newtons times 20 meters times cosine of 36.9 degrees, which is equal to 80,000 joules or 80 kilojoules. The work done by the force of friction is the force of friction times displacement times cosine of the angle between the two, which is 180 degrees. That is 3,500 newtons times 20 meters times cosine of 180 degrees. That is minus 70,000 joules or minus 70 kilojoules. So then the total work done on the load or on the sled is equal to 80 kilojoules minus 70 kilojoules. That is 10 kilojoules. So here I used the approach of finding the work done by each individual force and then adding all works together to find the total work done. Let's do the other approach, which was to find the net force and then calculate the work done by the net force. I just need to calculate the net force in x direction because in y direction the net force did not do work since the displacement is perpendicular to that force. But in x direction the net force is the component of the force in the chain parallel to the displacement minus the kinetic friction force. So this is 5,000 newtons cosine of 36.9 degrees minus 3,500 newtons. That is equal to 500 newtons. From here, the work done on the sled and the load is equal to the net force in x direction times the displacement. So that would be 500 newtons times 20 meters. That is equal to 10,000 joules or 10 kilojoules. In this example, I will use the work-kinetic energy theorem to calculate speed. So this problem is related to the previous example with the sled being pulled by this tractor. Let's suppose that the sled's initial speed v1 is 2 meters per second. What's the speed of the sled after it moved 20 meters? The work energy theorem states that the total work done on the object or body will be equal to the change in its kinetic energy. We also found in the previous problem that the total work done on the sled was 10 kilojoules. The change in kinetic energy will be simply mass times final velocity squared divided by 2 minus mass times initial velocity squared divided by 2. One thing that I don't know right now is the mass of the sled and load, but I know the weight of the sled and load. So therefore I can find the mass by simply dividing the weight by gravitational acceleration. So this is 14,700 newtons divided by 9.8 meters per second squared. This will give me 1,500 kilograms. Now let's combine all of that information together to calculate the final velocity of the sled. So we have 10,000 joules is equal to mv final squared divided by 2 minus mv initial squared divided by 2. So from here we have mv final squared divided by 2 minus 1,500 kilograms times 2 meters per second squared divided by 2. So from here we get that mv final squared divided by 2 is equal to 13,000 joules. From here, solving for the velocity, that is square root of 2 times 13,000 joules divided by 1,500 kilograms, which is equal to 4.2 meters per second. This problem can also be solved using kinematics only by using the relationship v squared is equal to v0 squared plus 2 times a delta x. This can be used because we know the initial velocity. We can calculate the acceleration by using Newton's second law, since we know the net force acting on the sled and the mass, and then the displacement we also know. Now I want to do one more example, and that is an example of motion with a varying force. An air track glider with mass of 0.1 kilograms is attached to the end of a horizontal air track by a spring with a force constant of, or spring constant of 20 newtons per meter. Initially, the spring is unstretched and the glider is moving at 1.5 meters per second to the right. Find the maximum distance d that the glider moves to the right if the air track is turned on so that there is no friction, and if the air is turned off so that there is kinetic friction with coefficient of kinetic friction mu k equal to 0.47. Here is the drawing of the problem. So this is the glider, this is the air track. The glider is attached to a spring. For the first part of the problem, where there is no friction, the air track is turned on. This is the free body diagram of the glider. So the glider is subject to the action of the normal force, its weight points down, and then the spring force. In the second part of the problem, where there is friction, the glider is under the action of normal force, force of kinetic friction, and the spring force. The weight of the glider pushes down. So for the glider, we know that the initial position is equal to 0 because we start looking at the motion when the glider is in a position where the spring is not stretched. And then we know that the glider displaces a distance d. So we know that the work done by the spring force on the glider will be minus k x squared divided by 2, and x will be the distance that the glider will travel, which is d. So the work done by the spring force can be written as k d squared divided by 2 and a minus in front of that. On the other hand, the glider experiences a change in velocity, which means that its kinetic energy will change. So the glider initially has some velocity, 1.5 meters per second, but when the glider travels distance d, it will stop. How do I know that it will stop? Because the question asks, what's the maximum distance that the glider will travel? What does that mean? It means that, and because the glider is connected to the spring, as it moves away from equilibrium, the spring starts to pull back with the spring force, and so therefore the glider will be slowing down until it stops. So if I were to sketch the situation, it will look something like this. Initially the glider is here, where x is equal to 0, that's the initial position, and then the glider moves a distance d to this final position, and at the initial position the velocity is 1.5 meters per second. At the final position the velocity is 0 meters per second. So then the kinetic energy final minus kinetic energy initial will be simply 0 minus mv initial squared divided by 2. And so the work done by the spring force will be equal to the change of this kinetic energy, because there are no other forces acting on the glider. So minus kd squared divided by 2 will be equal to minus mv initial squared divided by 2. From here we have the distance will be equal to mv initial squared divided by k under a square root. Substituting the values for mass, velocity, and the spring constant, I get square root of 0.1 kilograms times 1.5 meters per second squared divided by 20 newtons per meter, which gives me that the distance that the glider will travel to full stop, the maximum distance, is 0.106 meters. Now let's look at the second part of the problem, where the air track is turned off and the glider is under the action of kinetic friction force as well. This situation. So the glider is moving to the right. The motion is opposed by the kinetic friction force and the spring force. So when friction is also part of the problem, part B, in the statement of the problem, the total work done on the glider would be the work done by the spring force plus the work done by the kinetic friction force. The spring force does a work given by the first term here, and the work done by the kinetic friction will be Fk times displacement d cosine of 180 degrees. So finally the total work is given by minus kd squared over 2 minus mu k mg d, this expression here. And so this work will be equal to the change in kinetic energy. The change in kinetic energy is given by the same term as before, because the glider stops at that distance d from the initial position. So we have the total work done by the two forces acting on the glider is equal to the change in kinetic energy of the glider. Rearranging the terms and cancelling all the minus signs, gives me kd squared over 2 plus mu k mgd, and this here should be a minus mv initial squared over 2 equal to 0. I did that because since I'm solving for the distance, I noticed that I have a square dependence in this term, linear dependence in this term, no dependence in this term, so this is a quadratic equation for the distance. Solving the quadratic equation gives me this solution, which of course is two different solutions, 1 meter plus, 1 meter minus. Let's see what they are equal to. Substituting all the values in the expression here gives me minus 0.02303 meters plus minus square root of 0.02303 meters squared plus 0.01125 meters squared. Solving for d gives me two solutions. The first solution is 0.086 meters. The second solution is negative 0.132 meters. The second solution is not a real solution since the displacement is in positive direction. And so the answer to the question, when the force of friction is also turned on, the glider will displace a distance of 0.086 meters. And so with this, I am going to conclude the lecture on work and kinetic energy.